Hi, everybody. Okay, as our last video. So we have already established this much. We have vector spaces U and V finite dimensional. We have a transformation going between them. But U and V being finite dimensional are isomorphic to Rn spaces. T being a linear transformation is equivalent to a matrix transformation between these Rn spaces. So we have basically completely changed we view those objects. The only thing left is sometimes the matrix of T relative to the bases is just difficult to understand. It's difficult to understand what it's really doing to the spaces. So you may wonder then, are there particular bases that we should use so that the matrix transformation is simple to understand? And that's the question of similarity. And also then we lead right into then diagonalization, because if it's possible to diagonalize a matrix, it's the easiest representation for matrix multiplication ever. So if you have a transformation going from a finite vector space V back into V, where you're going from a basis B to a basis C, C and B are both bases for the vector space V. And you might want to know the matrix of T relative to C. Is it related to the matrix of T relative to B? And the answer is yes. And in fact, it's really easy. The matrix of T relative to C is a product of three matrices. The inverse of the change of basis matrix from C to B times the matrix of T relative to B times the change of basis matrix from C to B. And that's a similarity relationship between those two matrices. The standard matrix of T, the matrix of T relative to C, and the matrix of T relative to B. It's a similarity relationship. Why it's true is incredibly easy. So if you take the transformation T, it's exactly the same as saying, take the identity transformation composed with the transformation T, composed with the identity transformation. But that means then I have two transformations, linear, that are equal to each other. So I can then find their matrices relative to the bases. On both sides, I'll find out what they are relative to C. Now on the left-hand side, the matrix of T from C to C, that's just the matrix of T relative to C. On the right-hand side of a composition, so I have this other basis B that I'll use. So using the theorem I've given you before about compositions, the right-hand side can be written as a product of three matrices. It's the matrix of the identity transformation from B to C times the matrix of T relative to B times the matrix of I, the identity transformation, from C to B. Now, thing is though, is that the matrix of the transformation from C to C is just the transformation of T relative to C. The matrix of the transformation T from B to B is just the matrix of the transformation T. The matrix of the identity transformation from C to B is the change of basis matrix from C to B. So then we get this. And then finally, you remember that the inverse of the change of basis matrix from B to C is just the matrix, the change of basis matrix from C to B. Because of that, I get that. And that's the result I needed. That's a way of relating these two matrices of the transformation. It's a way to go, I don't like the current matrix for a certain transformation relative to a basis. I want to know what it is relative to a different basis. It's really great, it's really easy. In particular, it's really wonderful if we can find a matrix, a basis C, so that the result is a diagonal matrix. So if it's possible to find another basis B, so that the transformation, the matrix for that transformation relative to B is a diagonal matrix, then we say that the transformation is diagonalizable. It's really easier just to show you the process of like diagonalizing a transformation. It's literally just diagonalizing a matrix. That's all it is. And then at the end, you get a new basis to do the transformation. So let's look at the transformation from P1 to P1. Now, P1 is a two-dimensional object. So we have the two vector spaces. We're already thinking These are isomorphic to R2. So in our head, we interpret this as planes, two planes. And the transformation is going between polynomials, but down here, it's going between two vectors, a vector of size 2 and a vector of size 2. There's just a matrix that does that transformation. So the transformation is applied to the vector a plus bx, and it's equal to a plus b plus 2bx. I'm going to use the standard basis for P1 to get the initial matrix for the transformation relative to E. So just doing that process, the matrix of T relative to E winds up being the matrix 1, 1, 0, 2. Now that matrix is obviously diagonalizable because there's only two eigenvalues, 1 and 2, and their algebraic multiplicities equal their geometric multiplicities. They have to be 1 for each of them. So that's definitely a diagonalizable matrix. And in fact, the diagonal matrix you get would be the matrix of eigenvalues, and the matrix that does the diagonalization, that would be the matrix of eigenvectors. But here, though, interpret that now. It's not just a matrix. It's not just a matrix. It's actually a change of basis matrix that goes from the basis B to the basis E. That matrix then actually tells you what the coordinates of this new basis is relative to E, because the very first basis matrix, the very first basis vector would have coordinates. I'm trying to find my pen right now. I don't know what happened to it. Oh, there it is. The very first vector in the basis, we'll call that V1. So V1 would be in the basis. It would have coordinates relative to that basis, and that vector is E1. So if I take this and I multiply it to that, you would get the coordinates of that vector relative to E. So that would be the first column. So actually the columns that you see in that matrix, those are the basis vectors for B, just relative to the basis E. All right, good. So then using that, the standard matrix, the matrix of T relative to B is just formed by doing that similarity, that multiplication, and it winds up being the diagonal matrix 1, 0, 0, 2. And the change of basis matrix going from B to E, that's the matrix I gave you, 1, 1, 0, 1. That means then that if you want to know what the basis is, I gave you the coordinates of those vectors relative to E. Those coordinates are the columns that you found in that matrix, that change of basis matrix. So the coordinates of the first vector is 1, 0. So that's the vector 1, because remember the basis is E, 1x. So the coordinates of the second vector in this basis is 1, 1. So that would be 1 times 1 plus 1 times x, that's 1 plus x. So the basis we're talking about is 1 and 1 plus x. That if I find the standard matrix, if I find the matrix of the transformation, but relative to this new basis B, it will be a diagonal matrix, being 1, 0, 0, 2. Now, you need to be able to see a picture of kind of what's going on. Please remember at all times, all I'm doing is changing the representation of everything. I'm not changing vectors. I'm not changing spaces. I'm not changing the mapping. I'm not changing how things are mapped. All I'm changing is how they look, that's all, or how I call them. So then, P1, two-dimensional, it's like a plane. There you go, a plane. So the basis for that plane is I and J. So I just drew an I and J for you. The transformation is on P1 that we can't see right now. It has this mapping. Well, but that transformation also has a matrix of that transformation relative to this standard basis. The standard basis being 1x. And that corresponds to I and J in the plane. So if you wanted to, for example, let's take the image of some vector in this vector space. So the vector in the vector space is a polynomial of degree 1. So that vector could be like 3x. 3x, though, has coordinates relative to the basis. those coordinates would be 3, 1. So in the plane, I draw the corresponding vector that connects to the vector 3 plus x. That vector is 3, 1. So then the transformation, if you want to use the formula, the transformation would then give you transformation of 3 plus x is 4 plus 2x. I just drew in the corresponding vector relative to the basis E in the plane. And that would then be the vector 4, 2. Now, if you don't believe me, you can also look at a different way, because we could do the other path to do evaluation. I could find the coordinates of the transformation applied to 3x relative to E by finding the matrix of T relative to E, which we know it's that square matrix 1, 1, 0, 2, times the coordinates of the vector 3 plus x relative to E. That's literally just doing this matrix multiplication, and that's the vector 4, 2. So you can see then up here between P1 and P1, I mapped the function 3 plus x to 4 plus 2x, but I have to bring it down to what's equivalent to a different way between R2 and R2. I have a vector 3, 1. It got mapped to the vector 4, 2. Cool. Okay. The problem is that this picture, while you can compute it, I can figure out what the image is. You don't get a feeling, though. You just don't get a feeling for what is this mapping doing? Like, I get it on this one instance, but in general, what is it doing? The problem is that the matrix that represents this transformation is just not easily understood. But if it's a diagonal matrix, it's much easier. Let's do it again. So remember, the basis that diagonalizes it is 1, 1 plus x. So 1, 1 plus x corresponds to the vectors 1, 0, I, and then the vector 1, 1, I plus j. So then those two vectors I drew for you, and then they define their own axis system like this. That is just a different way to represent points in this plane. The plane being the representation of P1. All right, cool. So, but the transformation, the matrix of it relative to this new basis is that diagonal matrix. All I got to do now is show you how to interpret what that multiplication means. To do that, I need everything relative to the basis to understand. So if you have just a generic polynomial, in this case, first degree, it can be written uniquely in terms of some scalar times 1. That should be a 1 there, not x. 1, because the basis is 1 and 1 plus x. 1. Oops, go back, stop that. 1. There you go. And some scalar times the other vector in the basis, 1 plus x. So if you were to go find out what the coordinates are of P of x relative to that basis, those coordinates would be C1 and C2. So the image of the transformation applied to this polynomial, if I want to know what its coordinates are relative to B, I find the matrix of T relative to B, and I multiply it to the coordinates of the vector relative to B. That is literally doing that multiplication. So the coordinates of the mapping are C1, C, and 2 times C2. So the mapping T applied to this polynomial has to be given by a linear combination described by those scalars. Now notice what happened. Compare the original vector and the new one. Look at the new vector. The original vector had this scalar times 1, and the new one has this scalar times 1. Notice that component of the vector sum doesn't change. But the other component was C2 times the vector, 1 plus x, and now it's 2 times it. I doubled that component. Okay, let's look at the picture. Do you have an idea what's going on? So I'm going to go draw in the vector, which was 3 plus x. So 3 plus x wound up being that vector right there. Also, I decomposed it in terms of the two vectors in the basis. So 3 plus x is 1 plus x, that's the diagonal, and then 2 1s. 2 1s. So it's 1 times 1 plus x, and then 2 1s. So the coordinates of the vector would have to be 2 1. 2 1s, and then 1 plus x. So then if I apply the transformation to this, though, what it does is it takes the component corresponding to x, which is the vector going this way, and doesn't change it. Doesn't change it. It takes the other vector in the direction of 1 plus x and just doubles it. So let's just draw that. Remember now, see that length going this way, it does not change. The other diagonal one will double in length. That becomes that. And notice that when you take the blue vector plus the other blue vector, this one doesn't change, this one doubled in length, we get the original blue vector, the vector I had before. We have the exact same mapping. So this then helps you figure out then what the transformation is actually doing to the plane. In this case, the vector space of linear functions. It takes the space of linear functions and it stretches them in one direction and it keeps another direction still. This direction that it doesn't change is in the direction of the constant 1. The direction it stretches in the plane is the direction of 1 plus x. I can say direction because we have an understanding between mapping vectors in P1 and vectors in R2. So you have that geometric understanding. So you can make those analogies. That's neat, right? Because we were able to diagonalize this matrix, we have an idea what this mapping does to every vector in the plane now, not just the one example I did. Okay, last thing. So as a fun example, you can use these techniques to figure out the standard matrix of various mappings, or really any kind of mapping you want, as long as you're going from a vector space back into the same thing usually, because it's easier to understand there. So I've already shown you how to find projections. I've already given you how to find the standard matrix, basically, for a projection of a vector upon a line. We're going to do it all over again, because this technique is much more powerful than when I did the first time, because the technique I'm about to show you, you can use it on anything to get any kind of mapping you like, as long as you're clever about it. So I want to know, how do I find a transformation that will map everything to a projection on a line, where the line's going through the origin? To do that, I need a vector that describes the direction of the line. We'll call that D, like always, the direction vector. And I need a vector then orthogonal to it, because I need a basis for R2. So if U and D are two vectors in the plane and they're orthogonal, they instantly make a basis for R2. You can then easily figure out then, how will this transformation apply itself to D and to U? The transformation applied to D has to give you D back, because D is already on the line. So projecting on the line is the same thing. Notice that D can be written as a linear combination in terms of D and U. It's 1D plus 0U. T, the projection applied to U, since U is orthogonal to the line, that means that projection goes right to the 0 vector. And the 0 vector can be written as a linear combination of D and U. Now, from now on, please pretend that U and D are unit vectors. So if they're unit vectors and they're orthogonal, then that forms an orthonormal basis for R2. And we'll use the order DU in that order. So that means that I can find the coordinates of T's image on D relative to the basis D, and T's image of U relative to the basis D. It's literally just a linear combination. The scalar is using that linear combination. So the matrix of T relative to D would have to be the matrix 1, 0, 0, 0. So that's unfortunate relative to this weird basis that we don't know, right? Because we don't know D is, and we don't know U is. We don't really know what that is. But that's okay. We can easily fix that. Now let's try to find out, what would this matrix be relative to E instead. So I want the matrix of T, but relative to the standard basis instead. Okay. Well, to do so, I need to form a similarity relationship. So I need the change of basis matrix going from D to E, and I need the change of basis matrix going from E to D. Going from D to E is the easy one. The other one's just the inverse. So to find that, I take the basis vectors in D, and I find out what they are relative to E. Well, but I never told you what D and U were, right? I never told you how they're represented. So we're just going to say that D already is in terms of E. So that means then the coordinates of D relative to E is just D, because the coordinates of 1, 2 relative to E are 1, 2. Same thing with the coordinates of U relative to E. We're just going to assume that U already is relative to E. So that means that the coordinates of U relative to E is just U. So we get that matrix. That's easy. So if I wanted to know then, what would then be the change of basis matrix from E to D? That's the inverse of the matrix I just gave you. So that's unfortunate, though. I have to find the inverse of that thing. Oh, but I don't, though. It's not that difficult because I know the columns of that matrix are orthogonal and unit vectors. That's not just any old matrix. That's an orthogonal matrix. So for an orthogonal matrix, finding the inverse is easy. All you do is take its transpose. So I take the transpose of that matrix. So columns become rows, and you take the transpose of them. So then the inverse is, the first row is D transpose, and the second row is U transpose. Great. So now I can find out the standard matrix. The standard matrix of T is the matrix of T relative to the standard basis, E. But that is, by the similarity, it'd be the change of basis matrix, D to E, times the matrix of D of T relative to D times the change of basis matrix going from E to D. And again, if you need to, notice the way the things line up. So then the D, the D, the D, see how they're all the same? And what's left over is E. So you're going from E to E. That would then be the matrix of T relative to E. So then that matrix multiplication is that product. The first two matrices on the left, I just multiply them together, and I wind up getting the matrix D and the vector 0. That is lined up perfectly for the outer product method of doing matrix multiplication. It's row column times row. It's column row times column row. So then that gives you that multiplication. But 0 times U transpose is just a 0 matrix. So the answer is D times D transpose. So if I want to know then what's the transformation? The transformation, which I for some reason changed to be P, and just be T. The transformation applied to V is the matrix D times D transpose times V. And that's exactly the same thing I got before. It's just a different way to do it. This method, though, does not rely upon formulas and manipulations of the projection formula and recognizing that certain dot products are actually matrix multiplications. This can be done in general. So you can use this exact same idea to find all kinds of other transformations on spaces. I believe that's enough for that video.